very excited to be here. As we mentioned, we're both Physics and Astronomy students at UVic, and we are going to be sharing our work that we did with our professor over the past 4 months when we were working with her this summer. So we're going to talk about a few different things tonight. We've kind of broken it into a few different categories. We're going to begin talking about spectroscopy and ghost. And I'm going to pass it over to myself to continue. So one of our first things that we're going to talk about is spectroscopy. So spectroscopy is really the tool that we use in our research. I kind of want to first begin and talk about different spectra that we really see in astronomy. So let's say that we take a continuous light source, say this one on the left over here, and then we take a spectrum of it. So we're going to split the light that we receive from the object into a rainbow. You can use a prism to do this, and what we end up receiving is this really nice continuous spectrum. There's no gaps, no breaks in that spectrum. If we were just to look at a star directly, say without any interference of the atmosphere, we would just see a continuous spectrum. There's a few different other types of spectra. The other one is an emission spectrum. So let's say you have light that is again coming from a star, you have starlight, and then there's maybe a nearby cloud of gas. If the starlight is going to heat up the gas, and then you end up taking a spectrum of that cloud of gas, you end up with those lines that are kind of coming up. So we call this here an emission spectrum. The other one that we receive is an absorption spectrum. And that is the one that Riley and I utilize. Here we actually have lines of light that are being absorbed. So if there's something in between us and a nearby star that is absorbing these wavelengths of light, then we can use that to figure out, say, what's being absorbed, and we can also use that to figure out what things are made up of. So we can't go out and directly touch stars, but we can actually use spectroscopy to learn a lot about these stars. We can figure out how fast they're moving, we can figure out what they're made up of. There's a lot of different things that we can receive with the tool of spectroscopy.
Different elements give off different unique spectra. Up here you can see the sun's solar spectra. Depending on the atom that we're looking at, you can actually identify what is within the spectrum of an object. And this is the sun spectra. This also continues with galaxies or even gas clouds. Up here, you can actually see several examples of different spectra in the visible light. You have carbon, oxygen, nitrogen, iron, hydrogen, and helium. Depending on what you can, in this case is the emission spectra, you can see each emission lines. And this is really helpful because it's like a very unique thing you can see on each of the spectrums. Overall, studying the spectrum of stars or objects in the sky is very useful and a very powerful tool.
Okay, so we figured we'd begin and play a little bit of a game just to make sure everybody's on the same page. As students, we are required to test our audience. So at the very top here, we have an unknown gas, and then below it, there are spectra of helium, oxygen, neon, argon, and xenon. And I want us to put our thinking caps on and try to figure out what the unknown gas is. I can't hear you. Neon. Neon, you got it. All right. We're going to up the ante just a little bit more.
Okay, so this one, as you can tell, is a lot harder. The observed spectrum up here is in fact made up of several different spectrums. And so the last one was neon. Which one of these spectrums can you see within the observed spectrum? So, in fact, one of them that is not helium.
Hydrogen.
Oh, yeah.
Hydrogen. So, again, the answer is helium, oxygen, nitrogen, and argon.
This is
Okay, so we're all on the same page, did really good. So we're going to continue. So we talked about spectroscopy. So spectroscopy, we're really just studying the light that we receive from stars, and we get a lot of information from that light. The next thing that we wanted to tie this into is GHOST. GHOST is not what you think it is. It is actually a spectrograph. It is located at the Gemini South telescope over in Chile. It stands for the Gemini High Resolution Optical Spectrograph. We're really creative with our acronyms here in astronomy. We really try to make things work. But this is the instrument that takes all of our information for us. So it's located at the 8.1 Gemini meter telescope. If you know your constellations, you know Gemini means twins. So there is another telescope located over in Hawaii. But our group was guaranteed 200 hours of observations because our group was part of the commissioning team who had built the spectrograph. Just a little bit down the hill, they had done a lot of work building this spectrograph, and it got installed, I believe, in 2022. The light that we receive from Gemini is actually, from GHOST is in the optical wavelength. So it's around about from the 300 to 1,000 nanometers of light. So our eyes can receive light that's about 400 to 700 nanometers. So we just kind of go past the visible spectrum in the both ends. So we kind of get light that comes from the infrared as well from the ultraviolet.
Now, what can you actually do with the spectrograph like GHOST? Well, there's this interesting, I guess, effect where for sound or waves like sound and light, there's something known as the Doppler effect. Now, most people have actually experienced the Doppler effect. On my way here, I actually drove past the ambulance. And as you see on the right here, you can see the source, which in this case is the ambulance, and then the sirens. As the sirens move towards you, you experience a higher pitch noise. And as it moves away, it's actually lower pitch than what you would observe if you were within the ambulance itself. And this is very useful because, as I said, this works also with light. And the term used for the speed in which, the wave itself is moving towards you or away from you, it's called radial velocity. And, well, this also works with, sound, but in this case with light. This property of the Doppler effect and the radial velocities is very important to the project that we worked on, GHOULS. GHOULS. What is GHOULS? I know it does sound a bit scary, but GHOULS just stands for Ghost Ultra Faint Legacy Survey. And, well, we're studying ultra faint dwarf galaxies. This survey, GHOULS, is aimed at studying some of the faintest satellites to the Milky Way, ultra faint dwarf galaxies. Through this, we are studying the chemical properties of these UFDs. As well, we are studying the radial velocity values for the stars within these UFDs. Both of these are very important for understanding the makeup of these galaxies, which in this case are very, very old and very faint. The project GHOULS has been going on for a few years now. Many graduate students at UVic, including another undergraduate student, have also worked on this project as well. Some of the stars in GHOULS, in these ultra-faint dwarf galaxies, have had previous analysis done on them, but some of the stars are more new, like they're newly discovered as being a part of these ultra-faint dwarf galaxies, and have had no previous analysis done on them. And the goal of GHOULS is to understand the chemical evolution of ultra-faint dwarf galaxies. But what are ultra-faint dwarf galaxies? It's a good question. Ultra-faint dwarf galaxies are the oldest, most metal-poor, and most dark matter-dominated systems in the entire universe. As a result of that, they are some of the least chemically evolved systems in the universe. Another thing, since they are super old, to put in perspective how old these systems are, I believe the solar system is like 4.6 billion years old. Some of the stars in these UFEs are 12 billion years old. Some of them go up to like 13 billion as well, and the universe has only existed for roughly 13 billion years.
All right, so we have a whole bunch of galaxies that we're interested in, and we want to narrow down the ones that we want to study. And we have a few different criteria that we have decided as a group that kind of dictate what ones that we want to study. So on the sky there, we have a whole bunch of candidate ones that we have. So those are the ones that are the little stars there. And then we have a whole bunch of other systems that may be ambiguous. Those might be globular clusters. Those might be some dwarf galaxies. But we really want to narrow down to the ones that our group are interested in. So we have a little bit of criteria. Of course, the first one that we really need to consider is the fact that our telescope that's taking our observations is located in the southern hemisphere. It's in Chile. So that means that any stars or any form of a system that has a declination that's less than 30 degrees, so up in the northern hemisphere, obviously we can't see. So that really takes out a large portion of the sky, of the objects that we can't see. Then we kind of go to a little bit more of the technicality side. Our next thing that we're interested in is the spread of the stars in the systems that we're interested in. Dwarf galaxies are really interesting in that their stars are often quite diffuse. And one of the things that we've decided for our criteria is we want the we have decided that we want the half-life radius to be just larger than 10 parsecs. So a parsec is just a distance measurement in astronomy. That means that about half the light that we receive from our system has dropped by about 50%. And this is just a measurement on the spread of our dwarf galaxy and how far out those stars are. So again, that takes out another portion. Our next one is we want our systems to have a smaller magnitude of -7. So magnitude is basically just a brightness measurement in astronomy. Absolute magnitude is truly if we put all of our things at the same distance, what does it look like? And for ultra-faint dwarf galaxies, a galaxy having a magnitude of -7 is actually quite faint. And that's what we're really interested in. We want to know like what are the really faint things. And of course, there's not a lot of stars in these ultra-faint dwarf galaxies because they're quite old. And that's another key factor for deciding what systems we look at. And then the last one is our surface brightness. Surface brightness has to be greater than 26 mags per arc second squared. Again, we won't really worry about the technicalities of that. But really diffuse galaxies are going to have really low metallicities. That's what we're interested in. And so we've ended up with a very small region on our plot over here of the galaxies that we are interested in. And we get about 30 satellites. So we really cut our number quite significantly down. We started with a lot of systems. That initial plot had a lot of things on there. And now we've kind of limited ourselves to about 30 satellites that we're interested in.
Now that we have went over the criteria for GHOULS, what was our role in GHOULS? My work in GHOULS was initially doing data preparation on the data we received from GHOULS, and then I would do radial velocity corrections. And then after that, I would also then do signal to noise measurements. We will be describing what these are in a bit.
And then my work over here, I was taking the spectra of the stars, and I was first measuring the iron abundance, so how much iron are in the stars. I was also doing the signal-to-noise measurements, and then at the very end, we decided to do a little test to figure out how many exposures we want on the star, what's kind of the optimized value. So we did all that work over the summer, and I think we're going to go through in detail and kind of discuss what the results were.
Data preparation. The data that we obtained from GHOULS was split into two different regions of the spectra. As you can see up here, there is the blue region and then the red region. Once we have the data actually downloaded, what we would do is we would, for both the blue and the red region, we would fit a line to it, and then we would flatten the data into a normalized spectra. If you can notice here, the flux up here ranges from about 0 to 1500, but after normalization, it would only be dropped back to 1. After we normalized each of these spectra, what we would then do is we would stitch them together. So the blue region on the left side and the red region, once they were both flat, we would just put them together and we'll have one large continuous spectrum for each of the stars. Once we had a flat, normalized spectrum, continuous spectrum, I would then do radial velocity corrections. As described with the Doppler effect, because these objects were moving away or towards us, the spectra that we would obtain from GHOULS would have a shift in its wavelength. And that is why it was so useful. What we would do is we would look at a small region on each of the spectrum and notice the shift that we see. And depending on the shift, we would then correct the radial velocity. This was actually done for several exposures of the same star, typically 3 or 4, and this depended on the star's magnitude. With each of the spectra all obtaining the radial velocity, we would be able to get a pretty good approximate value for the true radial velocity for each of the stars. One issue, though, that I ran into with the data from GHOULS is that there was sometimes data reduction features. If you notice on the left, this is what we should expect, a relatively flat spectrum. This is just a zoomed in part of one of the stars. But sometimes the stars would have noticeable bumps in the spectrum. And this posed an issue when trying to correct for the radial velocity. If you can imagine, if you're trying to look at the shift of the line, when it is hard to tell where the line is, you run into a few issues. This only affected a few of the exposures, and most generally it would happen in the red exposure. The blue was almost always unaffected, and it was just rather unfortunate. We never actually got to the bottom of this. It only happened, I believe, for a 2-month period where some of the spectrums were just not what they should have been. They had, as I call them, features. But, and moving past, just a unfortunate thing, one big discovery, a part of GHOULS, was that we found a new binary star. Now, binary stars, it's a system of 2 stars which orbit around a common center of mass. And in spectroscopy, this kind of affects the shift in the spectrum of the star. And so one of the stars that we were looking at, it had 3 different exposures. One of them was 6 months after the first 2, and there was a very big difference in its radial velocity value. Very specifically, the star was in the Bootes 1 dwarf galaxy. As I stated previously, some of the stars in GHOULS were over 12 billion years old. This star would be roughly 13.3 billion years old, which is very, very old for it to be discovered now.
Okay, so on my side, when Riley was doing all that, my first thing that I was tasked with doing is taking the signal-to-noise measurements of all of our spectra. So there exists this big spreadsheet out in the internet. And this is where we throw all of our information, all of the data that we obtain from our spectra. And there's a whole bunch of columns, but you can see that we've got 3 different columns for signal-to-noise ratios. We take those values at 3 different wavelengths of light. So a signal-to-noise ratio is basically saying how noisy is your data, how clear is your spectrum. When we take our star and we observe it, the signal that we receive is really the starlight. And then the noise really can be a combination of a whole bunch of different things that end up coming out in your spectrum. It could be temperature fluctuations in your instrument, it could be atmospheric effects. There's a whole bunch of things that could contribute to like an increase in the noise that you receive. And that noise ends up affecting your measurements. So we want to make sure that we have a control and we know how much noise is in our measurements. Oftentimes, the things that are on the bluer region of your spectrum, so that's the lower wavelengths, they're going to be a lot less clear. As you move up in wavelength, our data becomes a little bit clearer, and so you can see that our signal-to-noise ratios end up increasing. So this is a common thing that we need to make sure that we're aware of. But the idea is we're basically taking multiple exposures of our stars. When GHOST is observing, we usually take about 4 observations of our stars, and then we stack them on top of each other. And the idea is we're trying to find an optimized number of exposures of that star, so we're getting still the data we receive, but we're not maybe wasting a bunch of observing time. So I'm going to just pause that for a second. I'm going to move on to my other thing that I was tasked with doing. I was interested in measuring the metallicities of stars, the iron abundances. So on the right, there's the world's most amazing equation. X plus y plus z is equal to 1. It's very scientific. The idea is we're taking the mass fraction of hydrogen, we're taking the mass fraction of helium, and then astronomers are really creative and kind of lazy, and we chuck every other chemical into a thing that we call a metal. So we've kind of got 3 different combinations of things that we're looking at. We're looking at the composition of hydrogen in your star, we look at the composition of helium, and everything else. And in total, they all add up together to equal 1. Metallicity is really just a measurement of how much metal is in your star. If you have a lower metallicity, typically that is an older star, we call that a metal poor star. If you have a higher metallicity, you're metal rich, and that's typically going to be a younger star. So metallicities are really important. We can determine whether or not planets are going to host stars are going to host planets around them. It also affects how long a star is going to live for. So this is a really important measurement. So my task was basically to take our spectrum of a star and measure how much iron is going to be in it. Of course, I'm taking a spectrum that Riley has already radial velocity corrected, and it's normalized, so it's been processed, and now it's my turn with it. Out pops some information from our algorithm. We're learning a lot more about our stars. We can measure the temperature of our star. We can measure some other things. We call it surface gravity and microturbulence. I'm not going to concern myself with this. So when we think of our spectrum, the plot that I had showed you before with those absorption lines looks really nice and really clear. And unfortunately, that's not really the case. This is an example of what we call an RV standard star. So it's a radial velocity standard star. We know what it looks like. We know how fast it's moving. We have really clear spectrum of it. You'll kind of notice this line around 1 that's really nice and clear. It's well defined. You can see where the absorption lines are coming off of it. And it's a very nice spectrum to take measurements of. Of course, that's not what real data is going to look like. That's way too easy. Are you kidding me? Our data is a lot more noisy. If you take a look before, we had that really nice line at 1. Here it's pretty noisy. You can't really tell where that line is. We call that line a continuum. And basically the idea, what I'm trying to do, is shift the spectrum up and down by certain amounts to really measure the strength, or like the absorption of that line. By doing that, I am essentially measuring the amount of metal that's in the star, or the amount of that specific element. So for my case, I was only looking at iron. That was the only element that I was interested in. And I'm shifting my spectrum up and down to try to match the continuum that was maybe behind the star. Kind of hard to see. It's a bit of a guessing game sometimes. But I'm really just measuring the strength of the lines. And then out will pop a measurement. So with all that work, basically, where are we now? Well, we've gotten a lot of radial velocities for our stars. We have a lot of information about the metallicities of the stars, so the amount of iron in the star. But really, our future work is kind of taking us in a few different directions. We're still getting a lot of observations from GHOULS. Lots of different data is still coming in for the next couple of years. We're really interested in looking at a full chemical profile of these stars. So we're maybe looking at different elements and trying to figure out if some are enriched in a certain element. We have grad students who are continuing our work right now, as we were only just doing it for the summer, but we are hoping to continue it at some point. But our grad students are taking over for the meantime. Not our grad students. But we are going to continue to be the first eyes on our data and continue our work with GHOULS hopefully in the future. That's not over yet.
Now, our work in GHOULS was as we have just described, but we had side projects to GHOULS. My side project was determining the radial velocity 0 point of GHOULS, the instrument. We did this by testing, determining the radial velocity of another standard star. This standard star, we know what the properties are of it. We know, it is, again, pretty standard. And we also know what the radial velocity should be for this star. Now, one thing that I ran into, again, with this instrument, is that there was quite a bit of variance in the radial velocity values. Not enough to count it out completely, but it didn't really line up with what we should expect. If you can see here, these are 2 different days of exposures. There are 5 exposures on each of these days, and it's relatively consistent. And that's the case for both of these. These are both, again, separate days. But if you see this dotted black line, that line is what the average was. Now, we had 10 different days of exposures, 5 exposures for each day, and they ranged on the low end of about 14.7 kilometers per second, and on the high end, about 15.4 kilometers per second. The accepted value for the radial velocity of this specific star, which is HD 65907, is 14.96 kilometers per second. So it does vary quite a bit, about 0.3 kilometers a second either way. And we were also not able to get to the bottom of this.
So on my side project was, again, looking at the amount of exposures that were needed to obtain an optimal signal-to-noise ratio for our instrument and for our data that we're interested in. So I did a little bit of a test, and basically I kind of just ran the same analysis that I would often do with the regular stars. I kind of just took an individual exposure and ran it through and got my information. And then maybe I'd take 2 exposures of that same star, combine them, run that through. I repeated that with different exposures, and we have about 4 of one star. And so I kind of ran that through, and the idea was, can we get rid of one of our exposures so we have more time on other stars? And the answer was no. We need to keep those 4 exposures in order to have a high enough signal-to-noise ratio for the data that we're interested in. So that was a little bit of a side project that I had. And then my other side project was creating a group website. So if you can scan the QR code if you're interested in, it takes you to our website that I've created. You can find a little bit more information about the work that we do. Our group is a part of a bigger group called Near Field Cosmology. It's a research group based at UVic. And that'll hopefully get a little bit more information about that. So with that, thank you all very much for listening. I hope you enjoyed. Happy to take questions.
Lauren and Riley, a wonderful presentation. I'm a little bit curious about your process for reducing signal to noise. And you say you capped it at 4. Did you try beyond that to see if you were getting diminishing returns?
Yeah, we only had a maximum of 4 exposures on each star, so that was like our top. If we had more, then I'm sure it would obviously improve the signal to noise, but 4 was our max that we were setting for the amount of exposures on one star.
So were you limited by much on that?
Yes.
How old is the light that you're typically observing from these very distant dwarf galaxies?
All of these dwarf galaxies are satellites to the Milky Way, and I might not be fully correct, but I believe they're all within, let's say, 100 parsecs. Yeah. So they are, or 100 kiloparsecs. We're 8 kiloparsecs from the center. So 100 kiloparsecs around, and 1 parsec, I believe, is roughly 3.26 light years. So you can say roughly 300,000 years old the light would be, just based on its distance.
Could you briefly explain what you mean by satellite?
Satellites. Satellites are really any object, I guess, orbiting around the main object. So to use Earth as an example, the moon is a satellite to Earth. And I believe we would technically be considered a satellite to the sun. We're just planets. So a satellite, like a dwarf galaxy satellite, is just a satellite that really orbits around the Milky Way.
Is there a specific reason that you guys focused with absorption as opposed to, say, Vision spectrum?
The only reason that we get absorption versus emission is really just the way that we're observing our objects, because there's interference between us and the objects that light is going to be absorbed by any material that's in between us and the galaxy. And so really just whenever we look at stars, we're automatically receiving an absorption spectrum. So it's really just the way that it happens to be.